Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. Last couple of classes we were discussing about shape memory alloys and shape memory effect pseudo elasticity. Along this direction you may recall that we have classified various type of phase transformation and we have specifically discussed about martensitic transformation, which is very much important phase transformation in order to obtain shape memory effect. However, in case of a shape memory effect there are many different criteria has to be satisfied by a alloy and different aspect has been already discussed, like reversibility of the phase transformation, and from austenite to martensitic phase transformation there is a requirement that the strain, transformational strain should be accommodated by a specific twin variants only. Because once we cool a austenite and the austenite transform into martensite, we deform the martensite, and during that deformation one type of twin variants or twin type grows in expense to other, and we can develop that strain which again recovered during heating, because the whole martensite transform into austenitic phase. And in this week we are trying to discuss more on some of the case studies. Here case studies means some specific alloy system, and those alloy system what are the austenitic phase and what is their crystal structure, what is the martensitic phase and how they transform, and what are their transformation temperatures and how we can tune those temperatures. So, these are the very important thing, so that we can develop specific alloy for some specific purpose. And so, ferrous system we have already talked, and today we will talk about shape memory alloy in non-ferrous system. Here I show you a big table, and if you kindly have a look, the first alloy system is the silver cadmium, where the composition is lying around 50-50 or something like 44 to 49% cadmium, and the transformation occur from a austenite which has a B2 structure to 2H, and the transformation hysteresis is rather small, you can say 15 K, and this austenite itself is a ordered phase. So, this is something very interesting, that the austenite here itself is a ordered. Why it is interesting? Because once it transform into martensite, those martensite should have come back to its original or parent crystal structure, which should be again ordered. So, the direction of this transformation is important. I am talking about crystallographic direction. Now, in case of a gold cadmium system, very similar thing happen instead of silver cadmium. The structural change is also similar. However, with certain composition range, let us say from 49 to 50, it transform to a trigonal type of structure. Here trigonal I am talking about a martensitic phase, where it has a very small hysteresis, and then it is also a ordered structure. Now, the second category here, which is very important, is the copper based system. So, copper based system is very interesting, because we all know about copper zinc, yes, because 70-30 copper zinc, which is also known as brass and so on, they are very soft metal and so on, and so they are very much useful for various engineering and applications. But we can get this shape memory effect in a very different phase field. A different phase field means it has a beta structure which occur, let us say greater than 38 percent, and there this beta has a B2 structure which transform into a 9R type of structure, which is a martensitic phase. And we can also further tune some of these transformation temperature by adding some amount of silicon, tin, aluminium, or let us say gallium and so on. So, this is another very interesting copper based alloy system, whereas the second interesting copper based alloy system is on copper aluminium system, and here we purposely add nickel for some specific issues. We will discuss into detail, do not worry. In case of copper zinc, the parent austenite has a B2 structure, whereas a modified 9R type of structure, that is actually the martensite, and B2 is the austenite. So, this austenite is a D03, it is also a ordered compound that appear in a copper aluminium. That phase also here called as a beta phase, and which transform into 2H type of martensite. Now, similar thing also has occurred in copper tin and copper gold zinc system. However, we will not be going to detail of copper tin and so on. The third type of system, which is also very interesting, is a titanium nickel system. So, here this is little off from a 50-50 composition, where 49 or 48 to 51 nickel concentration. Here the austenite has again the B2 structure, which transform to a monoclinic structure, or sometimes there are some R phase also form. We will go into detail of it, and here the hysteresis is a little bit higher, and sometimes we purposely add copper to nickel and replace nickel in order to tune the transformation temperature once again, and here B2 is also a ordered structure. Then titanium palladium system is also important, and there are some indium cadmium and manganese cadmium system. However, one should keep it in mind that some of these systems or non-ferrous systems require some specific thermomechanical treatment in order to gain this shape memory effect or good shape memory effect. A good shape memory effect means that the strain, that is the deformation strain that is given to martensite can come back or can be reversed 100% only after some training or can be given to the parent alloy. So, these are some of the very important systems that we have discussed, and out of all these systems I specifically like to discuss these copper zinc, where beta is the parent phase and aluminium is added to copper zinc, and the second system is copper aluminium, where some amount of beryllium is added and some amount of beryllium or aluminium is added. Here it is actually a copper nickel and aluminium system, and the third system is the nickel titanium, where nickel titanium copper is also another system. So, all these we will go into detail of that, and let us try to understand this matter. Now, in case of a copper zinc system, if you look at the phase diagram of copper and zinc, this is the atom percent of zinc, and in y axis the temperature is shown here. This is actually alpha FCC copper region, where we produce brass, and here this is a very interesting beta phase that has a B2 structure, and if we cool down beta, then around this temperature, which is just somewhat above 450 degree to 500 degree centigrade, there is a transformation that occur from beta to beta dash. Here beta dash means that it is a ordered structure of beta, and since beta phase shows a shape memory behavior then you can always ask why not to simply take such a composition, right. Unfortunately, beta is a very brittle phase and there is no practical use of it. So, we have to develop alloys which contain beta, but to gain some extent of formability we need help of this alpha. This means that we need a two phase structure. And now, how to get a two phase structure here? So, here this is a domain where alpha plus beta will form. So, I simply take this region and show it here with 0% aluminum. Now, here the alpha phase lies, here beta, and you can have a look that now if we have to produce such two phase microstructure, I can choose some composition here or here, here and so on. So, this composition should go lying here. And now, if I go towards the right hand side, the problem arises that martensitic transformation is retarded and the transformation temperature goes down very below. How to read it? Here you can have a look that if I choose such a composition, the MS temperature goes very down or even sometimes it does not occur at all. So, I have a very less chance to choose such a composition here, or maybe if I need MS temperature which should be somewhat around 0 degree centigrade, and then I have to choose a composition which is here. And for particular such a composition almost I get very less fraction of beta and mostly I have alpha. That is also another problem, because there is a transformation in this temperature range where beta will transform into alpha plus beta, and the composition of beta will be shifted to the right hand side, okay, and of that beta there will be no transformation at all. So, in copper zinc system this is a major problem, means if I choose a copper 38.58% zinc, then the composition lies here and I may get a large fraction of alpha in order to attain a MS temperature here. However, the beta has a composition which will be shifted towards right, where there will be no martensitic transformation at all. And therefore, the idea came that whether we can tune this phase diagram in such a way that martensitic transformation temperature can be raised and we get a shape memory effect. And therefore, people added 4 or 6 atomic percent aluminum and added some aluminum, and I show here with two different phase diagram with 4% and 6%. Now, let us consider for the case of 4% aluminum. Now, you can have a look here that if I choose such a composition purposely, I will get a MS temperature. This is actually the line which represent the MS temperature. So, the MS means martensitic start temperature. So, the martensitic start temperature lies around 0 degree centigrade, whereas on the other hand here if you just draw a tie line, I will have a chance to get 50% of alpha and let us say 50% beta, and definitely during cooling this beta will be transformed into beta dash and we will get a martensitic transformation and shape memory effect. So, problem has been solved by adding aluminum to copper zinc system. So, this was the purpose of adding aluminum to copper zinc. Now, in case of 6% aluminum, the situation is rather much better, because I will have a chance to get a higher fraction of beta and less fraction of alpha. So, the further improvement can be done. So, here MS temperature lies around let us say 0 degree centigrade. And then the question arises whether we can add further and further aluminum or not, and that I will come into detail in the next slide. Now, the basic question that comes to our mind, as I said, that why we add aluminum to the copper zinc system, what is the purpose of it? Usually, as I said, that alpha FCC, this is alpha copper phase, which is actually the malleable phase, and it enable us to shape the alloy for during forming, or let us say if I want to produce some shape memory wire like wire drawing process. So, the alloy at a ambient temperature, this allows some formability. However, the two phase region like 50% alpha and 50% beta, that I have produced around 4 weight percent of aluminum. And this, the problem with beta is that if beta is very much enriched with zinc, then there will be no longer any martensitic transformation, okay, which I show it here in the last slide. So, therefore, after shaping we need to do some homogenization, because during quenching itself some defect will be produced, and defects means the large amount of point defect, they are not good sometimes, and so we need to homogenize around 800 degrees centigrade in the beta domain followed by quenching. So, during this homogenization and quenching treatment, it produces poorly ordered beta structure, which is not desirable, and it contain many vacancies, and to anneal out or remove those vacancies from the poorly ordered beta structure, we need some tempering operation and heat treatment around 100 degrees centigrade for some 30 minutes, so that we can get a very stable beta, which will be further transformed into martensite, and this is the basically purpose of adding aluminum. Now, there are definitely some advantage and disadvantages of this system. However, people mostly prefer adding aluminum in the range of 3 to 8%. Here a B2 austenite, which is the beta structure, it transform into modified 9R type of martensite, and this transformation 9R martensite, which is a thermoelastic in nature. A thermoelastic nature martensite has a feature that if you keep on cooling, the martensite nucleate and growth continuously, okay. And this type of martensite usually show a rather smaller hysteresis and very good shape memory effect and very good superelasticity. Whereas, if we go beyond 8% aluminum, then instead of this 9R martensite, we get 2H type of martensite. And the problem with 2H type of martensite is that it is not a thermoelastic martensite or non-thermoelastic martensite, which occur by a burst type. Okay. So, and it exhibit usually a relatively larger hysteresis, which sometimes may not be desirable. So, I show you a schematic heat treatment process that show how really to develop this copper zinc aluminum shape memory alloy and how to process them. So, the treatment require, let us say here this is a typical heat treatment schedule that initially we heat it up and then let us say 500 degree centigrade, and let us say here we again heat and cool and heat and cool. So, this is for where we begin the shaping operation, and after shaping the alloy or wire drawing or typical shape we want to achieve. So, this the after the shaping has been reached, then we go for some homogenization treatment of the beta phase, and therefore, we have to reach up to the high temperature beta phase. Okay. So, here this is the beta phase. So, we are talking about high temperature means here. Okay. Below this there will be a beta dash structure, please remember. So, once we cool it down, then we get actually at room temperature and higher temperature we get beta, and then we basically get this 9R type of martensite. And again the problem there that if MS temperature is somewhat in between 20 to 100 degree centigrade, then if this MS temperature is in between 20 to 100 degree centigrade and below there will be a martensite and here will be a beta dash and above there will be beta. So, there the initial after initial quenching we need to go for some sort of elimination of the vacancies. We have to do this is basically done by a reheating of around 100 degree centigrade. So, this is one very specific treatment that copper, zinc, aluminum system that actually require. So, here just as a schematic I show you that beta which will appear here and beta dash will appear somewhere here. So, this is beta dash and here will be the 9R martensite. Now, the second system that we are interested to talk about is copper aluminum nickel system. Once again here the phase that shows shape memory behavior is the beta phase. Again here I show you a diagram, phase diagram with copper and aluminum. Okay. So, please consider the beta phase field to be the dark region only, and the martensitic transformation temperature varies with the aluminum content, and therefore, the MS temperature is shown here. This means, if we increase aluminum content, then MS temperature actually decreases very fast. Now, what are other problems? Please have a look. So, the MS temperature in this region is quite high, and just by adding 4% aluminum it goes to 0. Now, let us assume that we may have something like 14 weight%, there 50 degree centigrade is the MS temperature. On the other hand, there is a competing eutectoid decomposition. How to read it? Here the beta will decompose into alpha and gamma 2. So, there is a eutectoid decomposition which occurred in competition with the martensitic transformation, and therefore, we have to tune the alloy so that this eutectoid decomposition must be retarded and martensitic transformation should be enhanced. This means, in a TTT diagram we must develop in such a way that the transformation bay should move to the right hand side for eutectoid transformation, and therefore, it has to follow in such a way. So, once again I just summarize the case here that in copper aluminum, where aluminum is less than 14% has to be chosen, and where if we go for higher concentration of aluminum, then 2H type of martensite will form, and it is very brittle and there will be no practical use. However, the stable phase field of beta that is shown by the dotted line here can be obtained by adding some amount of nickel. Means nickel is purposely added here, so that this phase field will move here. What will be the benefit of it? Because it retards the eutectoid composition, and the MS temperature is around 150 degrees centigrade we can obtain. On the other hand, this particular copper aluminum nickel system is very good, because the MS temperature is quite high and we can use it as a high temperature shape memory alloy. And so, if we have to develop such a shape memory alloy, then we can have a chance to develop a composition where the martensitic transformation is also somewhat acceptable and we will get a large beta phase field. And this is one of the very interesting phenomena in case of a copper aluminum nickel system. Now, in case of copper aluminum nickel system, we should look at some of the variants that appear. The martensite variants are important because we know about the crystallographic changes that occur in this particular case. The beta phase, which is told which the structure is D03, which transform into 9R or 18R type of martensite. Now, here this is the stress versus temperature axis. In case of a transformation which may also depends on a higher aluminum content, the H or hexagonal phase martensite may also be formed. Please have a look at different variant, which is shown here as a beta dash, beta double dash and alpha dash structure. These are different variant of the martensite and the different stacking sequence are shown here, where the empty bubbles are represent aluminum and the filled bubbles are the copper. So, these are the position of the copper atom and we introduce some stacking fault inside it, so that we get the martensite variants of beta dash structure. Here it is beta double prime and it is alpha prime. So, this is along the direction of 001 beta dash type of structure. So, all these structures are very much important in order to accommodate strain, because once we deform along this direction, then the strain can be accommodated by introducing the growth of one type of twin and fault in the structure. So, this is let us say the stress direction or shear stress direction along one of the direction. Now, the third alloy system that is very much interesting to us is the copper aluminum and beryllium alloy. One should keep it in mind that beryllium is very toxic. So, initially the system itself could be used for industrial purpose, but it cannot be used for any kind of replacement of bone or any kind of bio implant material. And here this is also again a beta, which could be transformed into a complex type of martensite structure, and the phase diagram is shown here in case of a aluminum percentage and specifically for 0.7% beryllium. So, this is the beta phase field and which will transform to alpha plus gamma 2. This is similar eutectoid transformation in case of copper aluminum system that I discussed just couple of minutes ago. So, if we choose 0.47% beryllium weight percentage, you can see that the martensite temperature, start temperature keep on decreases by adding aluminum content. If we increase aluminum content, means if I go into this direction, whereas if I keep the aluminum content as a fixed. So, here aluminum content as a fixed and MS temperature can be tuned from let us say something like 200 to minus 200 degree centigrade. This is a huge range. So, if I want somewhat like a 0, so 0.7% of beryllium, it will give us something like 0. Okay. So, the benefit of these copper, aluminum and beryllium systems, specifically beryllium can be added to tune the MS temperature by alteration of aluminum and beryllium content. On the other hand, beryllium has a large help and it assists that the eutectoid transformation temperature can be further reduced. So, this transformation could be retarded. So, we can get martensite very easily, and another advantage that martensitic start temperature can be tuned plus minus of 200 degree centigrade by very little fluctuation of aluminum or beryllium content. So, this also help for a large potential for the industrial use. Also, we need to shape this alloy above 600 degree centigrade, because to avoid formation of beryllium containing compound. This is a general disadvantage. So far we have discussed two major system, one is copper zinc, another one is copper aluminum. In case of copper zinc, we have seen that we need to add purposely some amount of third element, so that we can tune the transformation temperature. Very similar way in case of copper aluminum system, we need to add beryllium or some amount of nickel, 4% of nickel, so that we can tune this transformation temperature in order to get the desirable phases. So, in the next case studies, we will discuss and continue in the next classes. Thank you.